everyone started following. What is nothing? See, when you keep a positive charge here, this is the source charge, right? So due to this source charge, what is the electric field at this point, Pima? It is kq by r square, electric field at this point. It depends on the source charge. So if I place any unit positive charge at this point, how much it will experience a force? You know that. What is the path faced by this unit positive charge because of this big source charge? Okay, that path, that is an imaginary line. Okay, so that imaginary line we call it as electric field line. So if you place a unit positive charge at this point, what will happen? This source charge will repel this unit positive charge and this positive charge will move in this way. Okay, it is not necessarily it should move in this way because I have placed it in this way. You have to join the line joining. It will act along the line joining the centers as per the central forces. If you place it here, what will happen? Again here it will experience a force of repulsion. It will travel in this way. If I place it here, then it will experience a force. So the path traced by this unit positive charge is nothing but what? Electric field lines, and it is an imaginary field line. Okay, so it is a convention that we follow. So what is that electric field lines? It is a curve drawn such that the tangent at any point every point you can take or any point on it represents the direction of electric field at that point. Second statement I will explain, but it is an imaginary curve. And electric field line is a space curve. What do you mean by space curve? It is a three-dimensional curve, like a sphere. When I draw it, I can draw in this way. Okay, the unit positive charge may experience force that can be represented by the outward lines. Okay, it is a 2D, but actually it is a space curve. It exists in all the directions, 3D. Okay, so three-dimensional space curve. But it is purely imaginary or hypothetical curve. What does this second point represent? The tangent at every point on it represents the direction. So if you just consider that this is the electric field line, and at any point if you want to find out the electrical field direction, line direction, then what you can do, you have to draw a simple tangent. Okay, tangent you need to draw it. The tangent direction will give you the direction of electric field at that point. And now if you take it as A, then the electric field at A is given by this tangent. Okay, what is the electric field at the point B? Then what you have to do? You have to draw a tangent. The tangent will give you the electric field at that point B. Is that clear, ma? So, each and every point, the tangent will give you the direction of electric field. Is it clear or no?
Yes, sir.
Now, so for positive charge, how will you draw the electric field lines? This is the positive charge you are taking. So how the electric field is nothing but what? Force experienced by a unit positive charge placed at that point, right? So always it is with respect to the unit positive charge. So this positive charge will repel this unit positive charge. So the electric field will always be pointing outward. In whichever direction you are moving, the electric field direction will always be pointing outward. Because whenever you place a unit positive charge, it will experience a force of repulsion. So, this for the positive charge, this is an important diagram for both point of view. They have asked multiple times. Draw the field lines of isolated positive charge. So, you have it is always outward. For positive charge, isolated. Here no other charge is there. For isolated charge, it is outward. Clear? Similarly, for negative charge, if you want to draw, then how will you draw, ma? This is minus q. If you place a unit positive charge, will it experience force of attraction or repulsion? It will experience a force of attraction. So the electric field line will be pointing inward. For an isolated negative charge, the electric field is pointing inward. Clear or no? Because electric field at any point is found out using the test charge, positive charge. So whenever you place unit positive charge, negative means it will attract, positive means it will repel. So that's why this inward and outward comes. Okay. Is it clear? Shall I move to the next one? If you have both positive and negative charge together, that is system of more than one charge. Okay, system of positive and negative. So what will happen? For positive, it will be what? It will be outward. Correct? So you will draw it outward here because there is no other charge present here. So I can draw it simply. And here it is inward. You can draw as many lines you want, but the magnitude, it is up to you. You can draw infinite number of lines. That also I will teach you how to draw it. First, listen to this. But when this curve, see one line when it is coming here, what happens? This will exert a force of attraction towards this negative charge. So what will happen? This will be a force of attraction. So this, look at this. A positive charge, the electric field line is outward, and for the negative charge, electric field is inward. So the line starts from the positive charge and it ends at the negative charge. Yeah? So similarly, this line is supposed to go in this way, but because of the force of attraction, what it will do? It will start moving this way. Yeah? And here also it is supposed to move this way if no other charge is there in the vicinity. But what happens? Because of the presence of this negative charge, it will start moving in this way. Clear or no? So because of the presence of these charges, the electric field line changes its path. Clear or no?
Yes, ma'am.
See here I have taken the equal charge. Okay, so how to draw the electric field lines? If you just take one coulomb, one charge, okay, 1 Q, then if you draw only, you can draw any number of field lines. If you draw 4 lines, okay, then what is 2Q? How should you draw 2Q? It is simple. You have to draw 8 lines. The proportion should be there. That's it. Okay. So 3, 8. It is up to you. You can take 10 and 20 also. That is not a matter. The ratio should be maintained. Here for 1Q you have taken 4 lines. For 2Q you are taking 8 lines. For 4Q how much you will take, ma? Or 3Q how much you will take? It is multiplied by 4. Okay. So you can draw any number of field lines for a given charge. But that proportion should be maintained. Is it clear or no? Everyone?
Yes, ma'am.
Any number of field lines is possible. Next, with the system of positive and positive charge. So I am taking equal charge only. So 2 equal positive charge. As usual, you draw the electric field lines. It will be pointing outward.
Ma'am, can you scroll up for a second?
Yeah, sure. What happened? So here what happens, this electric field line is supposed to travel in this way, but here another positive charge is present. Seeing the positive charge, it will start repelling, so it cannot move in this way, rather it will turn its path towards this, correct? So similarly, another field line, if you take it, it will also change its path because of the force of repulsion. The same way, if you draw the electric field lines from the positive charge B, what will happen? Here also the same problem comes. Because of the presence of other field line, it will change its path. Is it clear, ma, this diagram? So what happens at the center of this thing, that is the midway between the two charges, what happens here? Is there any electrical field lines present over there? No. So the net electric field is 0, right? The electric field lines, because of the presence of another positive charge, it has to repel, so it changes its path, and here also the same thing happens. Because of that, there will not be any electric field at the center, that is at the midway between the two positive charges. So that's why we have learned that null point between two equal positive charges lie in the middle of the line joining the centers. This we have learnt already, right? The reason is this. Is it clear or no? Everyone?
Yes, ma'am.
Yes, ma'am.
Okay. Properties of electrical field lines. Electric field lines, okay? So these properties are important. So the first property is what? Electric field lines start from positive charge and terminate at negative charge, right? This is for a system of charge. If there are two unlike charges present over there. But for an isolated charge, what happened? In free space, that means charge-free region. In charge-free region, what do you mean by charge-free region? There is no other charge, presence of another charge. So in charge-free region, the lines are continuous without any break. This is one important MCQ, okay? In charge-free region, the isolated charge, due to that is electric field due to isolated electric charge will be continuous without break. What is the reason, ma? You know that electric field is given by kq by r square. So the electric field value is inversely proportional to the square of the distance. When r is infinity, that time only electric field will become 0, right? So this electric field line continuous without any break when there is no other charge. But in between, if you place any positive charge or negative charge, because of the another force, presence of another force, it may vary. It may change its. Otherwise, it will be continuous till infinity. Is that clear?
Yes, ma'am.
Good. So the second property is the tangent at any point drawn at any point on the electric field line, okay, electric field line gives you what? The direction of electric field. So if you draw, see for example, we will take the pair of positive and negative charge. So how we have drawn that? It
Ma'am,
starts
could you
from,
scroll up a little bit?
yeah. Is it fine?
Yeah, you can go down. You can go down a little more. Yeah, it's fine.
Okay. So here, how we have drawn it, ma? So it starts from positive to negative, okay? And then We have drawn in this way, right? Now, at this point A, I want to find out the electric field intensity. What you will do? Just draw the tangent. The tangent will give you the electric field intensity. And at this point B, if you want, you have to just draw the tangent. Draw tangent, you find out the electric field at that point, the direction of electric field. Magnitude is given by, you know that, Q by R square. Okay, electric field lines never intersect. In your class test and the first term test, you may get this question. The reason, okay, never intersect with each other. Basic question, okay, what will happen if two electric field lines intersect with each other? Consider these two are the electrical field lines, okay, electric field lines, they intersect. If they intersect, what will happen? At this point P, I want to find out the electric field. How will you find out the electric field direction? By drawing the tangent. So one tangent you will get it in this way, the other tangent will point out this way, okay. So at point P, you are getting two electric field direction, correct? At the point of intersection, this P, how many electric field direction you are getting? There will be two electric field direction, right? There will be two directions of electric field, which is not possible, right? At the same time, you cannot travel in two different directions. You can either travel towards east or west, correct? You cannot travel at the same time towards east and west. The same way, electric field direction can, that is only one direction is possible. Two direction of electric field is not possible. Is it clear, ma? Everyone?
Yes, ma'am.
Yes, ma'am.
Good. You know?
Yeah, ma'am.
Next. So next, try to understand it. Okay, it's very simple point. The relative closeness. See, first from where it starts and ends. The second one we talked about, the tangent, because to find the direction. Then the third one, these lines never intersect. Now we have moved to the relative closeness of electric field lines. This is directly proportional to the magnitude of the electric field. What do you mean by this? If it is crowded, then we can say that it is strength, the magnetic field is strong here. And if it is less crowded, we can say less electric field. Sorry, not magnetic field, no, electric field. We are talking about electric field only. Okay. So electric field lines, you can say. Close together means what we can say? Strong electric field. So if the electric field, parallel electric field, we have seen it in the previous class. So this is given by what? What happened to Kavya? Kavya, are you there?
Yes, ma'am.
Okay.
Can you hear me?
Yeah, I can hear you. Now, this is closed electric field lines, right? Even though it is parallel uniform, I told you what is this? Parallel lines, nothing but what? Uniform electric field. So, these lines are very close together. We can say that this electric field is strong. That is, the electric field is strong here. And you can take this kind of electric field also. So, this is non-uniform electric field. Okay. In this, if you observe, okay, at this point, okay, the electrical field lines are closer than this region, correct? So here the electric field will be stronger than the electric field at B. If I consider this as B and this as A, EA will be greater than EB. Is it clear?
Yes, ma'am.
So next point, Any other point did I miss? The electric field do not form.
The closed loop thing.
What? Pa?
The closed loop
Yeah.
point.
Electric field lines. Don't use lines of force, okay? It is misleading factor. Don't use that. Electric field lines always you mention. Electric field lines never form closed loops. Because magnetic lines of force never form closed loops, you have learned, right? So, but here electric field line never form closed loops. The reason behind this is it is a conservative force. The work done in a closed path is 0, okay? So, it never form closed loop because it starts at positive and it ends at negative. Again, from the negative to positive, it is not possible. Clear? But in magnet, what happens, ma? Outside the magnet, it starts from north pole and ends at south pole. But inside the magnet, it starts from south to north, right? So this is magnetic field lines. They form closed loop. But here, the electric field lines, they don't form closed loop because of the conservative nature. Is it clear?
Yes, ma'am.
So the next one is electric field lines do not pass through conductor. Just a minute, number of field lines I give you already. The number of field lines represents the magnitude, that is the relative closeness. Next point is electric field. The field lines do not pass through a conductor. What is the reason, ma? Inside the conductor, the electric field is 0. This we will learn it in Gauss law also. Electric field inside a conductor is 0. But you can simply explain this. Already I mentioned that if you just place positive charges, if you give charges to a body, what will happen? All the positive charges will go and sit on the surface of the conductor because of repulsion, right? So they don't sit together. They just reside on the outer surface of the conductor. So what is the charge present inside at the center of the sphere? It is 0. So the electric field line will also be equal to 0. Clear? The electric field intensity at the center of the conductor will be 0. Is it clear?
Yes, ma'am.
So electric field lines will not pass through a conductor. In this only you can add that the electric field lines are always perpendicular to the electric. I will write it in words only. The electric field lines are always perpendicular to the surface of the conductor. These points are important so that you can learn the Gauss law in an effective way. So don't forget these points. What does it mean? If you take a spherical conductor, then where you can draw the electric field if it has positive charge. So electric field for a positive charge is always outward. So if you want to draw any electric field, then what you should do? You have to draw a perpendicular from the surface. Okay, the electric field wherever you take, it should be perpendicular to the surface of the conductor. You cannot draw it simply anywhere. If you take any irregular shape, then what you have to do, find out first for this surface what is the perpendicular, draw that and then draw the electric field. Here if you want to draw it, first you draw the perpendicular and then draw the electric field. Here if you want to draw, what you will do, you have to draw the perpendicular and then you have to find the electric field. Electric field is always perpendicular to the surface of a conductor. Is it clear? Surface of a charged conductor you write. That will be the proper thing. Conductor can be neutral, right? For the charged conductor it is. Any doubt?
No, ma'am.
Okay. So electric field is said to be uniform. Uniform electric field. It's said to be uniform when ma? If the magnitude and direction of the field intensity remains same at every point. So how will you represent uniform electric field? You can represent in this way. Parallel lines. Okay. So if you have a plate, this is positive, this is negative. Then how will you draw the electric field? The electric field line should start from the positive and end at negative, correct? And if it is uniform, then parallel, equidistant line, parallel lines. So this represents uniform electric field. Non-uniform field, the reverse of uniform. Electric field varies at different points, or you can write varies from point to point. Point to point, either in magnitude or in direction. Both the way it is possible, right? So either in magnitude or direction or both. Non-uniform electric field lines can be converging, diverging, or both. So converging means what? See the arrow mark. Here the electric field lines are traveling towards this way. So this way, here it is converging line field, because here the electrical field lines are relatively closer than this point. Diverging means what? The same diagram, you can draw it, okay, by changing the arrow mark. Here they are moving apart from each other. Is it clear or no? Everyone?
Yes, ma'am.
Okay. So this question definitely you will get it in your class, school exams. Okay. So